Hello everyone and welcome to the official opening of the Photonic Integration Technology Center, a center which will advance innovations to solve global and societal challenges with revolutionary chip technology, or in other words, will advance innovations by using the power of light. My name is Irene and I have the distinct honor of being your host today, about which I'm really happy. And we are coming to you live from the city of Eindhoven, the city of light, how spot on, which together with Twente is one of the two home bases of the Photonic Integration Technology Center. And earlier today, the 4 founding partners signed their collaboration agreement. The 4 founding partners are independent research organization TNO, industry accelerator PhotonDelta, the Eindhoven University of Technology and the University of Twente. And them signing this collaboration really marks the beginning of the PITC and its mission to accelerate the industrial uptake of integrated photonics. And that's, of course, what we're celebrating this afternoon. We are also really happy that our first event is part of the 10th edition of the Dutch Technology Week, which puts the Dutch high-tech sector on the pedestal it deserves. And it lasts until Saturday. So many thanks to you for joining us on this beautiful day. And what do we have in store for you for the next 60 to 70 minutes? First, we'll be kicking off with a presentation by somebody you probably already know, Dr. Michael Lebby. He doesn't need an introduction, but I will try and give one nonetheless. Afterwards, we'll be hearing from 3 companies and organizations that work with photonic integrated circuits. And they'll be introducing themselves and their work via video. Afterwards, there's a special guest on stage. He is the managing director of the Photonic Integration Technology Center, to which I'll now start referring as the PITC, Erik van Geest. He will talk about the work of PITC and the team behind the organization. Around 4:15 p.m., we'll be ending the plenary session, but the event is nowhere finished because we'll be inviting you to network with us in the network section of your application that you're in right now. And I'll explain a bit more at the end. One more important note before we start, you are able to interact with the speakers. So if you go to the chat section on the left side of your screen, you'll be able to put in your questions. The moderator will send them to me and I'll be asking them to the speakers. Okay, let's get started. And how to introduce our first guest best. Dr. Michael Lebby has spent his career advancing photonics. He's played several roles in the industry, from research to manufacturing to investing, and even running the USA Trade Association in photonics. He is now the CEO of Lightwave Logic. And besides being a serial entrepreneur and an investor, he's also an inventor. He holds over 450 patents, mostly in photonics, and he was recently nominated to the National Academy for Inventors in the US. As you know, he has a great passion for photonics and integrated photonics in particular, and he is one of the driving forces behind the PIC roadmaps, the PIC roadmaps, which plot out where the technology is headed over the next decade. And although already elaborate, this introduction only scratches the surface of his experience. Dr. Michael Lebby is calling in from San Francisco, which we really appreciate because it's still very early on the west coast of the US. So Dr. Michael Lebby, can you hear me? And maybe more importantly, have you had your morning shot of caffeine?
Yes, I have. Thank you very much.
Okay, great. Thank you so much for joining us this early in your day. Dr. Lebby will be giving his perspective on how Europe can be successful in integrated photonics and PICs in general. Dr. Lebby, the floor is yours.
All right, thank you. Let's share the screen. Okay, just double check that you can see this. I don't hear any response, I think.
We can see and hear you really clearly and well, so you have the floor.
Okay, let's go. So I'm going to talk to you today about photonic integrated circuits and enabling our future. So I have a safe harbor slide because I work for a public company. The focus should be at the bottom of this slide. The orange bar is always a takeaway summary from my slides. So if there's too many details on the slide, just look to the bottom. And the slides will be posted at our website. There's going to be a little bit of detail here, so you can always check the detail afterwards. So sit back, relax. There's no need to take any notes. The agenda today, I'll look at the environment, I'll look at the markets, some of the technologies, and some of the metrics there. I'll take a quick look at some roadmaps, and I'll summarize. So there's 3 questions to remember today. Will photonics, PIC photonics, enable many things, and will it be part of our lifestyle? Is an interesting question. Will it be integrated just like ICs 50 years ago and become the engine for new designs? And the third question is will integrated photonics and PICs enable new products? So, you know, the impact here is lifestyle, integrated engine, new products. So let's take a quick review of the environment. The internet is a catalyst for a change in lifestyle. As you can see, we've gone from the old traditional computer-centric networks on the left to network-centric environments in the middle, and on the right-hand side, user-centric personal space, as you can see. And what that really means is we've gone from exchanges to data centers to hyperscale data centers. This is the use of heavy data. So our lifestyle has evolved towards personal space, and we've certainly seen that over the last couple of years. And in fact, there's a lot of data on this slide, but if we just focus on the left-hand side, what is affecting our lifestyle change? Well, certainly it's become virtual in the last 2 years, working from home. We've all experienced that. We've all used lots of data. Video is one of the big metrics here, and we've certainly seen a lot of new applications like augmented reality, virtual reality, headsets and things. But the bottom line, if you look at the summary at the bottom of this slide, is the video use of heavy data. That really has been the bottom line in what's changed our lifestyle. And in fact, if you look at what video has done to the internet traffic, this is just a couple of graphs here. This is interesting because Cisco predicts the internet traffic over the next couple of years. I mean, what do these numbers really mean? What does 400 exabytes per month or 4 yottabytes per year actually mean? And I've just plotted the normal table on the right-hand side where we go from kilobits to megabits, which is your internet at home, and gigabits and terabits. And you can see we're actually, in terms of traffic, we're on the red, which is yotta, which is 1 and 24 zeros. And that's the end of the international metric. It doesn't go any further than that. And so the bottom line here is that the virtual lifestyle is now the new normal. We're using lots of traffic, and video is really driving that traffic. So what are the new trends? Well, here's one new trend, which is really exciting. And this is automotive. This is LiDAR in cars. This is putting intelligence in cars, networking, LiDAR, sensing, lots of cameras. We're seeing that in some of the new cars today. But as you plot out over the next 20, 30 years, you know, these cars will have integrated systems. Those systems will need photonic integrated circuits and PICs. So when you start thinking about level 4 and 5, which is robotic type level cars, that fuels more data, and that goes into the data centers, and that's really going to be a lot of heavy data use. The PIC technologies that we are talking about today will benefit from this. So a quick look at the markets. Where are market opportunities and where are they growing? Well, we can see from this slide, there's lots of different photographs, different market applications that range from medical to bio to sensing to automotive, and the classic sort of high performance computing data centers and fiber communications. These are broad applications for PIC platforms. PIC platforms are platforms that send and receive optical data. We can see it's really broad. And as you look out over the next 10 years, and there's plenty of market forecasts. I tried not to put any particular graph in, but if you look out over the next decade, look at some of the sizes of these broad applications for PIC-type photonics. And you can see some big ones here. These markets are huge. And they're not just fiber communications and high performance computing. There are other applications too that are going to grow quickly over the next decade. This, to me, is really, really exciting. And so just take one of these market forecasts where we see fiber optic transceivers that do use PICs today. These are a perfect vehicle. And over the next decade, this is an $80 billion market in terms of total photonic components. The transceivers themselves are 2/3 of that market. So that's a huge opportunity. So the fiber optic transceivers explode over the next decade, and that's a great vehicle for photonic integrated circuits. And in fact, if you look at a lot of these transceivers today, there's a good combination of discrete optical components, but you can see the trend over the next decade is that you're going to see a lot more integrated components. That's more photonic functions on a single chip. And PIC-based transceivers will lead the segment by the end of the decade. And so this is an important metric, and this is a trend that we have to watch. So looking a little bit, this is data from Yole. This shows you some of the data rates that are used in transceiver modules. But what this slide really says? This slide says is the data rates go up from 100G today to 200 to 400 to 800G, which is just emerging. You've got the OBO, which is onboard optics. This is a huge opportunity for high performance, high speed photonic integrated circuits. And we can see already that PICs will be the engine for growth with these really high data rates. And this is just looking out from 2020 to 2026. So this is not quite the end of the decade, but you can see the trend is already emerging. So what are the technologies? So we have classic PIC incumbent platforms already. We have indium phosphide. I've also put gallium arsenide here, but indium phosphide is really quite the leader when you look in terms of fiber optics. We have the new incumbent, which is silicon photonics. A few years ago, it was a new technology, but today it's reasonably mature. You've seen it in products. The revenues are growing quickly. But also there are new platforms, and there are hybrid accelerators for PICs. And these are different materials that will enhance the performance of the incumbents already in place. So these are things like polymers, dielectrics, glass, lithium niobate, thin film. You can see the list here. There's a big list of new platforms that will actually increase the performance of PICs as we look forward over the next decade. Silicon photonics, as you can see from the takeaway, is the new kid on the block, but there are plenty of new platforms. And that term for the new platforms is called hybrid PICs, and it's becoming more popular around the world. And so what are the global players and their PIC platforms today? This is an interesting chart that Yole brought out, I thought was really good. You can see the growth of silicon photonics. Those are the green boxes around the world. You can see now a trend of hybrid platforms with new technologies with the different colors. And so the question we have to ask ourselves is what combinations of technology make sense for hybrid PICs? And the takeaway is the challenge is to further PIC performance with other materials. And so there is a trend towards hybrid PICs with different materials. And in fact, if we look a little bit closer here, we can see the two incumbents. We've got indium phosphide on the left, we've got silicon photonics in green on the right. And you can see some of them have good attributes and some of them have limited attributes. Indium phosphide, it's really tough to do big VLSI circuits. And in silicon photonics, obviously we don't have the laser. And so the incumbent technologies can't do everything. And so we have to look at hybrid PICs. How do you complete that performance portfolio? Hybrid PICs can boost that performance by adding things like modulators and AWGs and different types of passives and even lasers. And so we're going to see both indium phosphide with new materials. We're going to see silicon photonics with new materials. And these are hybrid PICs. And so another important metric, if you start talking to some of the folks here in California, the big data center folks, less than $1 per gigabit per second will open new markets for PICs. This is a cost performance metric. And so you can see from the graph on the left-hand side, the customer expectation is less than $1 per gigabit per second. So what does that mean? That means if you had an 800 gigabit link, an optical link, and you wanted to meet the challenge of 50 cents per gigabit per second, which is what the challenge is today, that's buying that link for $400. So that's $200 for one end and $200 for the other end. That's really tough to achieve. So that's cost performance. And the only way I can see and folks can see that technologies can close that gap and accelerate that cost down in terms of dollar per gigabit per second is using photonic integrated circuits. And so that is a vehicle that's really going to provide the solution as you look at these super high data rates. And also, when you start looking at these things in terms of PICs, as the complexity increases, you'll need more semiconductor, just like you did in silicon ICs. So there is pressure. This is a graph that shows the trend of indium phosphide PICs in terms of die size, the size of the semiconductor. The same is going to apply for silicon photonics. There's pressure to increase the wafer size for economies of scale. Hybrid PICs will allow both indium phosphide and silicon photonics create competitive PICs in the next decade, and so that the industry can achieve the cost speed metrics through PIC platforms. The interesting trend over the last few years is that silicon foundries, these are the CMOS fab plants, they are hungry for opto business. And so they want silicon photonics. There's new upside here. And these foundries use things like PDKs, the process development kit. And so these PDKs will drive hybrid integration of PIC platforms. That's what's allowed to be run in these big plants. And you're going to see these big plants not only do silicon ICs, you're going to see them doing photonics and PIC platforms too over the decade. And the drive to 200 and 300 millimeter allows competitive PIC cost per volume. And the cost is something we have to keep our eye on as we scale the industry. So let's have a quick look at speed. Can we make PIC devices faster is an interesting question. And so the traffic capacity, I'm using a road analogy here. And so we started off with the rough roads, and then we made roads better by paving them. And then we added more lanes for traffic capacity. So we did the easy things in our industry, and we added more lanes and we paved the road. And then we wanted to send more data down the same lanes or channels. So what did we do? We sort of essentially stacked cars on top of each other. And what that really means is in our industry is that more symbols per bit. And so we can send more data down the same channel. So if you think about it, our industry has already done the really tough stuff like stacking cars on top of each other by using things like higher order modulation, PAM4 and QAM, and you see that today. But one of the things we're stuck on is speed. You know, we're still stuck at 60 miles an hour. So we may have 10 lanes of freeway, but speed has hit a plateau in our technology, in our optical technology. And so let's have a look at where the issues are. Speed is actually limited by conventional photonics device designs. And this graph is a 3D graph, and on the vertical is modulation, and on the horizontal is speed, and in the depth is parallel. But you can see I've done a red dotted line and a green wall. And you can see those colored spots. Those are spots where you have commercial products, and the optical devices only go 30 to 40 gigahertz in terms of bandwidth. And you don't find devices to the right of that red dotted line. And if you look at the box on the right-hand side, you know, 3 dB bandwidth for the 35 gigahertz device is 50 gig NRZ, or it's 100 gigabaud PAM4, which is where the industry is today. So our speeds of optical devices are limited. The question is can we get the optical devices and PICs to go faster? Well, can we get to the right of that dotted line? Can we get 70 gigahertz PICs? Can we get 70 gigahertz devices? What does that actually mean? That's double the speed. That's 100 gigabits NRZ, or that's 200 gigabaud PAM4. And so that is sort of one area that the industry is lacking. Can we go faster? And in fact, I mean, there's some new technologies like the one I'm working on, which is polymers, optical polymers. They can break the speed limit. And I'm just showing you some of our latest results on the right. You can get bandwidths over 100 gigahertz. That means you can start thinking up at the potential of 200 and 300 gigabit type solutions. And so faster PICs alleviates a lot of the circuit complexity in networking systems. So there is a drive and there is a need to have faster devices and faster photonic integrated circuits. So let's have a quick look at packaging, because this is another trend that's going to evolve quickly over the next decade. Can we package PICs just like IC electronics? Well, let's have a look inside of a data center real quickly. You can see what the corridors look like on the bottom left. You can see the faceplates in the middle. You can see one rack on the right here. And you can see that rack has pluggable transceivers that plug into that front faceplate panel. And that equipment capacity is limited by how many transceivers you can fit and plug into that faceplate. So you have size constraints here. And the faceplates limit the flow of data, just like a blocked artery. And so the question now is how do you get more data in and out of that faceplate? Well, looking at to rethink, to unblock that artery, a lot of industry is now thinking about, well, we have pluggable transceivers on the left on that green figure that plug in, and we're looking down on the printed circuit board here. And those pluggable transceivers connect with that blue square, which is the switch IC, which is the electronic IC. And we know now that the pluggable transceivers are not scaling with data flow, which is on the left. But as you move to the right, you can see onboard optics with purple fiber bringing the optics closer to the IC. And then you see co-packaged optics, which actually brings the optics intimate. It gets the optics right to the IC switch chip. And so that now means you have to think about photonics integration of both the electronics and the photonics. And you can see the takeaway from this slide. Co-packaging and chip scale packaging are now considered inevitable. A lot of the big companies, a lot of startups are now working on this. So co-packaging is a theme that's going to accelerate over the next decade. So now let's have a quick look at roadmaps, just like Nostradamus in the 16th century. And so certainly this was the work I did with PhotonDelta a few years ago, and I think it was fabulous work. And I think what I'm trying to do here is to really explain it quite simply. And so what the work was is you look at years in the horizontal, in the vertical, you've got product vehicles, and in the lower vertical, you've got technologies. Very simple metrics. And then on the left-hand side of the roadmap, you have black font, which is normal R&D funding, where you expect the technologies that will progress. And then on the right of the roadmap, which is basically a decade out, major investment in R&D to achieve those goals. And in the middle of the roadmap, you have a purple brick wall, which means a technology cost barrier. And so that means is you may have already the photonics technology to achieve the performance, but not at a cost for commercialization. So you've got to think about the cost as well. There's no point in having an optical computer that costs you $1 million when you really want something that's under $1,000. And so also an optical computer may take a lab size, but you want something the size of a microprocessor chip. And so the next slide is what the roadmap looks like. There's a huge amount of data, and it's in one page. And I like the one pages because you can use them in presentations. So I would encourage you to, if you want to look at the details, look at it online. But think about this, roadmaps provide a vehicle for all the stakeholders, whether it's government, industry, academia, bankers, investors, etc. And you can see here, there's a lot of detail here. I'm not going to go into the detail, but let's have a look at the trends of the purple brick walls, which I've colored in purple. The top purple arrow shows that that purple brick wall is a little bit to the left. And that means it's really tough to design things like 1600 gigabit transceivers. Now, some of the devices can actually go faster than 70 and 80 gigahertz. And you can see the purple brick wall has moved to the right as you look lower down. So some technologies have higher performance. And so the question is how do you penetrate this purple brick wall to get to where the red font is, where you get the really high performance and you can achieve your goals for industry. And so the next thing I'm going to show, which is actually brand new, is I like one-page roadmaps. And so I think now we need a one-page PIC packaging roadmap. And so rather than review all the details here, you can see them online. And this is a draft of which I'm working with the EPIC folks, and I'd like to work with you folks here as well as PhotonDelta. What does a one-page PIC packaging roadmap look like? And I think this is going to be an important sort of roadmap for the industry to see where things are going very quickly and very efficiently. And so let's have a quick look at some European observations in the last couple of minutes. So positioning for PICs. Well, in the USA, we have a large silicon foundry platform with government funds that's aimed for photonics. As we've seen over the last few years, that's been suitable for defense contractors and large corporations. There hasn't been a lot of SMEs utilize this facility because it's very expensive. And that's silicon photonics. In terms of indium phosphide PICs, we have companies like Infinera, Lumentum, 26. These are not true foundry-like. So it's very difficult for SMEs to actually access this type of technology. In Japan and Asia, we have huge silicon foundries hungry for silicon photonics. You've got the TSMCs and the HiSilicon and the Samsungs, etc. These are suitable for large companies with big silicon photonic platforms, but if you're an SME and you've got an innovative platform, it's really difficult. And in terms of indium phosphide in Japan and Asia, you've got PICs with Fujitsu, NTT, Sumitomo. These are not true foundry-like, so it's also difficult for SMEs to get access to indium phosphide PIC technologies. And in Europe, we have a mix of large and small foundries that are all hungry for PIC leadership. And in fact, EU has deep experience with PICs and certainly works really well with SMEs, small and medium-sized enterprises. So how does Europe win with PIC-type technologies? Well, we already have some interesting investments here. The EU has made broad investments into PIC photonics and R&D over the last 30 years. There's been an early focus on indium phosphide, silicon photonics, and hybrid core competencies. And today we have, for example, PIC pilot lines in Europe. These are small focused PIC photonic teams that can scale to manufacturing and become self-sustainable. I've certainly participated in many of these pilot lines. Foster these types of projects to commercialization, and perhaps with a hub spoke type architecture where the pilot lines are the spokes, and then maybe you have a hub that really focuses on bringing all the technology together, maybe a really good direction. And in fact, to create leadership, how do you win here? Obviously, you've got to provide easier access for SMEs because they really drive the innovation in this technology. You've got to be able to create a sharper focus on hybrid PIC performance and foundry and packaging, especially co-packaging and chip scale, just like the silicon electronics industry have done. You've got to have PIC design infrastructure, and you've got to have PIC manufacturing. And I believe you need to make and create more PIC pilot line scale projects that impact not only fiber optics today, but the growing markets like auto, automotive, medical, sensing, display. And that will actually end up into building a global center of excellence. And I think that can be done in Europe because Europe has already had the big investments in PIC technology already. And so just to summarize, so the three takeaways I started with that we want to remember, will PIC photonics enable our lifestyle? Yes, certainly from the heavy data today for virtual networking to enabling new market opportunities. We've seen this in consumer and health and bio, etc. Will photonics be integrated like ICs? Absolutely. The PIC engine will be the next generation IC, and that, I believe, will be the PIC. And then will integrated photonics enable new products? Of course, and we can see already new and exciting products. And I'll leave you just with one thing. Why drive a horse buggy on the left-hand side when the motor car is available on the right-hand side? And I think we have to think very clearly that the PIC platform over the next decade or two is going to be the new engine. It's going to be the new motor car. Thank you.
Thank you, Dr. Levy, for this elaborate presentation. 3 questions have come in through the chat, and I just want to remind the people who came in a bit later that you can leave your questions in the chat for all the presenters, and we'll ask them here on stage. So I'm going to read out the first question. You already mentioned the EU investments, of course, in your presentation. The question is, there are European-level initiatives, pilot lines that aim to upscale photonic technologies. What role could or should an applied research center like PITC take in order to benefit the photonic industry as a whole, according to you?
Well, I think you need to look at the trends that are happening in the industry, and we can see the trends are towards high speed, lower power photonic integrated circuits. And I think you need to figure a way to thread the pilot lines together. I think we'll need more pilot lines because I think there's gaps. 7, 8, 10 pilot lines are not enough. I think you can see already the broad industry applications are going to use a PIC engine. And so a Photonic Integrated Technology Center, PITC, can certainly look at the gaps that pilot lines have left and help fill those gaps and make sure that you can provide a center of excellence. So when the big clients, the big customers, they could be data centers, they could be hospitals, they could be medical companies, want to come and look for the next engine, they come to the PITC, they come to Europe in general, because that is where the solutions are.
Great.
In details, you can see each pilot line has different technologies, but I think you can sit back and look through and see, well, there's a couple of gaps here we need to fill.
Great. Okay, so identify the gaps and bridge them, indeed. A very specific question. Is it already possible to fabricate PICs on the 200 millimeter or 300 millimeter wafer size? I hope I pronounced it correctly.
Yes. Indium phosphide, for example, doesn't come in 200 millimeters, but silicon goes in 200 and 300 millimeters. And so we're now seeing smaller pieces of material being put to 200 and 300 millimeter silicon platforms. So I think we should start thinking about the silicon platform as a low-cost vehicle where we can add higher performance through different materials technologies. It could be indium phosphide, it could be glass, it could be dielectrics. It could be barium titanate, for example, it could be polymers. And so thinking about the 200 and 300 millimeter silicon wafer as a platform is a really good way to think about advancing the performance of PIC platforms. That's not to say you can't use indium phosphide. I think you can, and I think it will be. But one of the things indium phosphide suffers is getting to the large wafers. So I think there's creative ways to do that, and this could be one of them.
Great, thank you. Do you think that new front-end lithography tools are needed for integrated photonics? For integrated photonic chips? What resolution performance do you think would be needed?
So the answer is yes. And as you advance photonics, you are going to get to the nanometer scale. There's no question about that, especially when you have optical waveguides and you want to split and combine waveguides. You're now looking at dimensions that are in the sort of 10 to 100 nanometers. Even some of the optical devices like slot modulators are down to less than 100 nanometers. And so if we really want to think about effective PIC technologies as we move forward, you have to start thinking about these types of line widths. And that's really pushing the state of the art in some of the big CMOS fabs today. So yes, the answer is absolutely.
Great, thank you. Last question, a bit more generic. You already mentioned in your key takeaways, of course, it will happen. But when will consumers, or when may consumers be expecting truly integrated electronic photonic integrated circuits in daily life in smartphones, laptops, cars, and refrigerators?
Well, that's an interesting question. We already have an iPhone with a big gallium arsenide chip with 300 VCSEL lasers on it. Whether you want to call that a PIC chip or not, I don't know. But it certainly has all the optics. It doesn't have the electronics. And so the question is when we're going to see both electronics and photonics. I think over the next decade, we will see more of this. Maybe at first from a hybrid scenario of actually bringing the photonics to the silicon chip, just like we saw in the co-packaging slides. And I think we're going to see more of this. And this is really going to force people to think about how do you integrate both electronics and photonics. And so that's bringing the photonics closer to the electronics. It will happen. And probably you will definitely see products by the end of this decade. We probably will see prototypes in the next few years.
Great, thank you so much. Thank you, Dr. Levy, for your presentation and answering these questions. You're going to stay on for the networking, right?
That is correct.
Okay, thank you. Thank you so much, and see you later this afternoon.
Right.
Okay, we are now going to continue with introductions via video by 3 organizations and companies working with photonic integrated circuits. These are the Chip Integration Technology Center, Signify, and Smart Photonic.
Hello, This is Barry P. from PITC Chip Integration Technology Center, located in Nijmegen. And as you can hear, our name is kind of similar than PITC. Well, first of all, I'd like to congratulate, of course, PITC for their opening. We are, of course, looking forward to cooperating with PITC. We have been aligning with PITC for quite a while. We share a partner. TNO is also a founding partner of CITC, focusing on chip integration and packaging from CITC. And one of our program line focuses on integrated photonics, where we are already working with different photonics partners like Fix and Tegema. And we do see in the future a lot of new cooperation opportunities together with PITC. And Erik and all of your colleagues, we're looking forward to extending our cooperation in the future. Congratulations.
My name is Jean-Paul Lennarts. I'm professor at Eindhoven University of Technology and I'm a research fellow at Signify. And I'd like to congratulate PITC and the team with the kickoff of the Photonic Integration Technology Center. And working for Signify, a company with more than 100 years of experience in lighting, we see a major revolution in the lighting technology. From heating up a filament, illumination products now have made a transition towards solid-state semiconductor lighting. But that revolution comes with many more changes. Light points become connected and become smart. Data connections, sensing and intelligence make the lighting infrastructure the largest Internet of Things network in the world. We see light as a new language with extraordinary potential for brighter lives and for a better world. In fact, light itself can also carry large amounts of data, but it is more than just an addition to radio communication. Laser light beams can carry data at rates that resemble the rates of optical fiber, and it can target the data precisely to the intended recipients. And thereby, optical wireless communication avoids all the interference that makes radio communication now sometimes make hiccups or have problems in very dense areas. In fact, Signify already launched optical wireless positioning systems in 2011 and Li-Fi communication systems in 2018. Both were based on LEDs. And we see an appreciation in the market for the quality of service with optical wireless, the guaranteed latencies and the absence of hiccups in the communication. But we like to keep innovating. We like to keep on improving the performance, and therefore we expect quite a lot from photonics. And therefore we are pleased to see new initiatives from organizations such as PITC that can help us forward. So let's make the city of light into the enlightened city of the photons. And with the launch of PITC, we're making a step forward in that direction. So I wish the Photonic Integration Technology Center a bright future, and I'm looking forward to explore how we can work together in an open innovation environment.
Welcome to Smart Photonics. As we all have experienced over the last year, photonics can be a big solution for data, for more bandwidth. So that's what we are working on. But next to that, photonics can be a solution for reducing energy consumption, for improving healthcare, for better sensing. And that's exactly the things what we are working on. As Smart Photonics, we are a pure play foundry for indium phosphide, which means we produce chips for our customers to help them improve their applications. So today I want to show you around our company. I will show you our people, I will show you our expansion, and I will take you along to tell you where we can collaborate with PITC. Here we are at the heart of our company, that is our people. We managed to grow the team significantly over the last years. We are now over 100 people, all working on to realize our photonics dream and working together with the people in the ecosystem to build photonics in our everyday lives. This is the entry to our clean room. This is the gowning where people dress up to go into the clean room that is behind me. In this clean room, that's where most of the investment of Smart Photonics has taken place. In this clean room, a team of operators and engineers work together to optimize the processes and to develop the chips for our customers. So here we are in the clean room of Smart Photonics. Here we produce our chips for our customers. We're developing and optimizing the processes. And this is exactly the area where we can collaborate with PITC to improve and to improve the offer for our customers. So here you see a number of tools that we have invested in. So the expansion has taken place and is taking place to reach a 10-fold capacity increase over the next year. So here we are with our latest acquired tool. And from this place, I want to congratulate PITC with its founding and look forward to a fruitful collaboration. So thanks, and I hope to see you all very soon.
Thank you so much to the companies. And I really love what Jean-Paul said. Let's turn this city of light into an enlightened city of photons. It was really great. Thank you. Okay, we're moving on to a really special guest right now. He is the Managing Director of the Photonic Integration Technology Center, Erik van Geest. Erik holds a PhD in electronics, and he started his career in Eindhoven because he worked at Philips for 11 years. He has vast experience in the high-tech sector due to several roles, one of them being at NXP for 14 years. And Erik will come on stage to give a short presentation, after which I'll be able to ask him questions, and you will be too, so please put your questions in the chat. He'll be introducing the work of the PITC and the people in the team. So Erik, welcome to your own event and your party.
Thank you, Irene.
I will join you in a second. The floor is yours.
Yeah, thank you. Well, everybody who is calling in to this event, thank you very much for being here. I also want to give a special thank you to Michael for the presentation he held, knowing that he had to get up awkwardly early on the West Coast. I also like to thank CITC and Smart Photonics and Signify for their introduction. And of course, we are also very much looking forward to work with them once we get started. So, for me, in the PITC, quite a lot of things come together from my career. I started working on robust design and reliability, and I had most of my professional managerial experience at NXP, where I was managing teams that did chip design. And for me, what has always interested me is that on one hand you have innovations, the real new stuff, to push the limit, to find out what cannot be done before. But on the other hand, also very much down to earth. Nice that it works on a lab table, but how can we make it work in a product? And how can we manufacture it with a high yield? And how can we make sure that it don't break down after a while? So all those things now for me and for our team come together. We will still work on those innovations, but we will also keep a close eye on what it takes to scale up to really industrial application. Let's take a look at what we can learn from semiconductors. Michael already made the comparison, and I think there is quite some interesting similarities. Semiconductors has been on a roadmap of more than 50 years of innovations, and in fact already a couple of years after this roadmap was first mentioned, people were saying that the fundamental physics would limit further improvements. And somehow we always found a way to overcome those. So that is a continuous stream of breakthrough innovations that took place. And I call it breakthrough because that were really things that before people could not imagine that could be overcome. And the roadmap is not just an expectation, a prediction. It has also set the pace for the whole industry. Michael also referred to the IP-SRI roadmap, where PhotonDelta is working together with MIT to basically set a similar pace for the advances, for the breakthrough innovations that are needed in integrated photonics as well. The other aspect of semiconductors is on the application side. So at the beginning, people could not even imagine all the things that are possible today. And in fact, there's also things that people did not just not imagine it, they did even not consider it useful. I'm thinking of there are those interviews that they did in the 90s, where they asked people whether they wanted a mobile phone. And people said, mobile phone? I have a phone at home. And when I'm not at home, then I have an answering machine. Why would I ever need it? Well, things have progressed quite a bit. And what we do foresee is that with the integrated photonics, next to the things we can already foresee right now, there will also be other things that at this moment we don't even know that we need it. And in fact, we would tell everybody that we don't need it. And I find it very exciting to be part of that. So let's imagine that we can have such new applications. Let's go to data centers. Michael already told about data centers, and of course we want the data centers to become faster and more capacity, and we've seen all those graphs. Another element is also the energy consumption, and we definitely also need breakthroughs on energy consumption. And what we think is that by putting things more in integrated photonics, we can also make a big step there. So with integrated photonics, we can help reduce the energy consumptions of data centers. Then other area which was also mentioned on autonomous mobility. What I always find striking is that basically everybody, almost everybody, can learn how to drive a car, but apparently it is really very, very difficult to do that in an automated way. Now, part of this is, of course, the processing part, to decide on what you need to do. I'm not going to cover that. But another part is also getting the right information to base your decisions on. Now, what if we could use photonics to get all the relevant information, feed it into all the algorithms, and then make the right decisions and have automated, safe mobility? Third element I want to mention is on the medical area. So when we make things smaller and more compact, we can measure more things and also do it in such a way that it does not all need to be done in the hospital. And this point of care, as we call it, will not only bring more convenience, that you don't need to go to the hospital, but it will also enable new ways of doing healthcare. And in that sense, integrated photonics contributes to more effective and affordable healthcare. Now, all great, but how are we going to do this? I want to bring you back to the similarities with semiconductors. We talked about the roadmap, that it's important, but of course it's also good to know what is behind that roadmap. One element of it is the breakthrough innovations, so the continuous series of breakthrough innovations that will be required. And that is also why we need all the universities to continue their advanced research and to push the limit and to work on, well, tomorrow's or even day after tomorrow's challenges. But next to that, there's also a few other things. In semiconductors, the fact that there is standard processes is a very important success factor. So you have a process and you develop a product. But because you develop a product based on a process, a standard process, you know that when you design it according to the design rules, it will have the right quality, it will have the right yield and also lifetime. And that way you can have a time to market which otherwise you could never achieve. It also goes the other way around. If you have a product, but your technology advances and you have a new technology node which is more cost-effective or faster or better quality, then you can port your product design to this new technology node. So this decoupling of process and product is a very important one. It also comes with things like simulation, which you do when you design a product, and you can do it even before you manufacture. The third element I want to mention is automation. So you cannot produce the chips with that complexity without the enormous amount of automation that is used in semiconductors. And that is something we will also need in integrated photonics. It's not just automation of the manufacturing, it's also automation in the design. So, for example, doing those simulations as I referred to. So, these are some aspects that is in the DNA of semiconductors, and I think we need to learn from that and translate that to how do we deal with that and how do we make use of that in integrated photonics. Well, that's a lot of stuff, and what we also learned from semiconductors is that no one can do that by himself. Even the bigger companies, they only take care of part of it, and you need an ecosystem to work on all those aspects and be sure you address those things. Well, Michael already told us that Europe is especially strong at these kind of ecosystems with small and medium enterprises rather than one or two big major players. Well, I always like to not call them small, medium enterprises, but scale up, because that basically tells a bit on the ambition. They may be small now, but the ambition is really to become big. But that is, I think, a point that we can leverage and that we need to work with. Now, this brings me to the PITC. PITC was set up as a cooperation between Eindhoven University of Technology, University of Twente, TNO, and PhotonDelta. In our team already we have Jan Laurens van der Steen from TNO, Pieter Telleman, University of Twente, myself, and then Yvonne van Kempen and Sylvester Latkowski from Eindhoven University of Technology. And with this team we will get started and get the first programs and activities going. I think Irene already mentioned bridging the gap. That is exactly the role that we have. Bridging the gap between research and application. And with that, we will help to strengthen the ecosystem, and we will also contribute to the IP-SRI roadmap, as was already referred to earlier. Well, but then more concrete, what are we going to do? We are going to do the technology development in what we call shared research programs. In those shared research programs, we will work together with companies, with universities, and tackle those big challenges that we can work, where we can be more effective to do it together than if everybody does it alone. And we will, where required, also enable or provide access to high-end facilities. And that way we want to lower the threshold for companies to enter into integrated photonics. Finally, we will work with universities and colleges on the curricula of the workforce we need, skilled professionals. And that will be on different levels, not just university people, but also on other levels. So, I think we are at a really exciting phase. Integrated photonics has a lot of potential, as we saw in the earlier presentations. The feasibility has been proven. There is small series manufacturing already at this moment. And scaling up to high volume is around the corner. Still, there's a lot of work to do, and well, I'm ready with my team to work on that, and let's embark on the journey. Thank you.
That was so great. Unfortunately, there's no one here to applaud, but otherwise I'm sure you would be getting a standing ovation. But I'm glad that we can also have a Q&A, and questions can, of course, still be submitted through the chat. I am curious, you mentioned the key role of the Photonic Integration Technology Center is bridging this gap from research to application and technology development, but can you speak to what exactly will the PITC do and what will it not do?
Yeah. Yeah, so as I mentioned, we will start with setting up what we call shared research programs. And maybe I should make it a bit more concrete. Mm-hmm. At this moment, we are already thinking of a couple of programs, being on the indium phosphide process technology, being on silicon nitride process technology, and also on what we call metrology, which is measurement and test. And each of those has, of course, very specific targets, mm-hmm. which we try to achieve. I just pick out one of them. In silicon nitride, for example, that is a technology that can be used, for example, in this medical sensor area, but it could also, or it can also be used in, for example, quantum computing. But in order to do that, you need to have very sensitive waveguides, mm-hmm. And you need to have a very efficient way to modulate the light, to sort of process the light. And today's technology that is, let's say, on an industrial level, does not have achieve that level yet. There has been research that proves that we can get further, but that needs to be made more mature. And that is one of the topics that we will take up.
And still making it more mature sounds a bit abstract to me. What exactly will you do? Will you be building prototypes, for example, or what is the work that the PITC will do, and what is the work that it will not do also?
Yeah. So on the technology side, it is really about achieving certain specifications and not just achieving them like on a lab table, mm-hmm. But also achieving in a way that you can produce it in larger quantities. So that
like a prototype, or?
And now that's the prototype is more on the application area. So technology is one thing, and then there is a lot of emphasis on this manufacturing and repeatability. Prototype would be more towards particular applications. So I think what was already mentioned, that some applications we foresee, but some applications we don't even think that it would be possible. Well, in order to unlock that, we will need to have prototypes where we show what can be done with the technology. So the prototypes we will also do, but that is more focusing towards particular application domains.
Okay. And you also mentioned the PITC will be providing access to high-tech infrastructure. Can I envision that I'll be in Twente and Eindhoven and I'll be walking into clean rooms with PITC branding on it, or?
Well, who knows? The starting point is this bridging the gap. So at the moment that there is facilities either at universities or by commercial companies that provide
already existing facilities,
then there would be no reason for PITCs to step into it. Mm-hmm. But knowing that will not automatically happen, and probably not in all areas, I think Michael also referred to that. That is the kind of things where we will step into. That also, we also believe that there is that can be a real accelerator for the success of integrated photonics, but it can also be a magnet for companies to basically join us and work with us on integrated photonics. So we will start with those shared research programs. So it's not that I'm now trying to find a building where we can make a clean room.
I understand.
But it could very well be somewhere in the future, and if not a clean room, then there is also other equipment, especially in measurement and test, that sits outside the clean room, but also is something that when you start in integrated photonics as a small company,
It's
you
unaffordable.
would not. It's
Yeah, of course,
unaffordable.
yeah.
Yeah.
Yeah, I understand. And you are you're a non-profit, but you do have a business model. And
Yeah.
who are your clients?
Yeah, so at this moment, we basically start here and also from the ecosystem that is around us and that we are trying to help expand. But our clients in the end are not just, you could say the local companies, but also very much the bigger companies that want to embark on integrated photonics. That could be that they want to embark on the technology themselves, but it could also be users of the technology. And for example, Signify, well, they have light as their core competence, so in that sense, it's spot on. But when it comes to integrated photonics, they see themselves more as a party that buys this integrated photonics, and then they want to look at others who can manufacture it and provide it.
And are clients just in the Netherlands, or
No?
No?
Well, again, at this we start from.
Of course, you're starting today.
I
understand.
Yeah. So, but the ambition is definitely worldwide, and I think that's also important. On one hand, you do need the local emphasis and create a hub, a technology hub, and the knowledge together. On the other hand, this is a field where things are happening around the world, and we need to collaborate and also try get our customers from everywhere.
I understand. Okay. One question came in through the chat. How and where can companies get in touch if they want to explore developing products based on photonic integrated circuits? So how and where can companies get in touch if they want to explore the development of products?
Yeah. So this is exactly the kind of things I was referring to, where this can be companies that maybe right now do something else, but want to enter into integrated photonics, or companies that working
and you want to stimulate them to enter, basically.
Yeah, and so I would say, well, get in touch with us, get in touch with me.
Eric at PITC.nl, or?
That is eric.vandegeest@pitc.nl. That does not mean that we as PITC can answer all the questions, but we definitely know the companies and the parties around us, and we can help get to the right expertise.
Cool. I have a question, because you just said you also have international clients. You are, of course, in the Netherlands, and you're partly publicly funded because your partners are publicly funded. So what is the role of IP? Because what if you help, say, a company in Germany, and then they develop a product that becomes amazingly successful, and they attract a lot of talent, and then will the Dutch government look to you and be like, hey, that wasn't the idea? How do you view that?
Yeah, it won't work that black and white. And in a way, Germany is still Europe. So Netherlands, I think, is also very small to only look at a Netherlands scope. But also it is really important to not approach it in this black and white way. So we do need to work together on a worldwide scale. At the same time, let's not be naive. Every region wants also to create and establish a business around it.
Yeah, I'm in the quantum space, and we also, when we are talking with other governments, they usually say the space itself is still so early in its development. There's no room right now for like country nationalism. Would you say it's the same for photonics? Like you need to work together in order to develop the industry as a whole? Yeah,
I think so. Usually I'm a little bit more skeptical on all those things, but it's anyhow, it is important to work together because the challenges are much broader. Hey, you can try do everything by yourself, and then if somebody else has found an alternative which is better, then you're completely out. Well, maybe it's better to work a bit together and then become better as a whole rather than only as one single place.
Yeah, understood. A question through the chat. At the Eindhoven University of Technology, there is the Institute for Photonic Integration, IPI.
Yep.
How do you see the collaboration between the PITC and the IPI? Will PITC complete the circle of supporting infrastructure for photonics in the Netherlands, or do you see or need room for more supporting elements?
Well, let's start with the first question. So IPI is really complementary. PITC will focus, we always call that the higher TRL level, so that is where you don't do the real fundamental academic breakthroughs, but you try to bring them to the point that it can be applied in an industrial way. And the IPI is on the academic side. So I really would love to have a continuous stream of innovations and new research idea and pushing the limits coming from IPI and also other universities, of course. And then PITC plays, I think, a good role for the universities as their outlet of where the technology goes and as a bridge towards application in practice. And if that is then sufficient or if we need more, I would like to park that question. We'll see in future.
Okay, great. Because you're starting out today. What is the first thing you'll be doing when you wake up tomorrow?
Yeah, so, when we wake up tomorrow...
After the party?
After the party. The first program where we are focusing on at this moment is on metrology. That is on measurement and test. And I always say that it may come across a bit like, hey, is that a relevant topic? Because it's not the hardcore of the photonic technology. But it is really very important. If you are not able to automate this test methods and to have real good relation between what you measure and you test and how the process technology looks like, then you will never be able to mass produce things. For example, in a silicon chip, if you would not have a way to test it in just a couple of seconds, you would never get a working chip out. So a very important topic, also very exciting. We are already, in fact, before the PITC, we were already working on a joint project with several companies on this topic. And we are very happy that at this moment we can sort of kickstart the PITC with a program that is based on that proposal.
Great. And when will the program launch?
That we try to launch it this month or next month.
This month already?
Yeah.
Off to a great start, I would say. Congratulations.
Thank you.
We're going to be watching the launch video of the founding partners who signed the collaboration agreement this morning.
Welcome all. Today we officially open PITC, the Photonic Integration Technology Center, a collaboration between the University of Twente, the Eindhoven University of Technology, TNO and PhotonDelta. It was a great pleasure that we are at this stage so far, after lots of work, that we're going to sign this document to stabilize the cooperation. Integrated photonics could well be the next big thing. It's technology that can sense, that can capture, that can process data at unparalleled speeds, efficiency and sensitivity. Similar to electronics, but now better, faster and more efficient. It processes photonics, photons and not electrons, and that's the big difference. The similarity though is that we integrate this in chips, which we now call Photonic Integrated Circuits, PICs. The technology of photonic integration offers a big opportunity for the Netherlands. We have a heritage in this domain. We have significant companies that are active in this domain. And yes, we have tremendous quality research in our universities in Enschede and Eindhoven. And that, together with the support from the government, creates an ambition to be one of the world's leading players in the area of integrated photonics. So it's with great pleasure that now we can have PITC as the next element in realizing this ambition. PITC is created to bridge the gap between research on the one hand and application on the other hand. To bridge the gap between research on the one hand and market on the other hand. It's by bringing together those parties in these areas that we can take a next step in realizing our ambition to use this fantastic technology to create the products that the world needs tomorrow. Having said that, it is my pleasure now to sign the collaboration agreement and take a next step in the ambition of PhotonDelta. Here we go. This is my signature, and I pass it over to my colleague.
Thank you very much. Well, as one of the founding fathers of PITC, the Eindhoven University of Technology is extremely proud to sign this agreement. An agreement which we signed in a very special year because the Eindhoven University of Technology is celebrating its 65th anniversary. And I'm looking forward to an intensified cooperation in the field of photonics with all our great partners. I'll sign the agreement and then pass it on to our next partner. Here you go. Thank you very much.
The University of Twente is a proud member of PITC. We think we can contribute a lot because we have a lot of expertise in manipulating light. So one of our top researchers, Professor Pepijn Pinkster, actually considers photonics to lead to a very safe future because it can lead to safer internet connections and unhackable ID cards. So I'm going to sign now the agreement. And I will now hand over to the next founding partner.
For more than 90 years now, TNO has been boosting industry and society and well-being with its innovations. And what I see now is that photonics becoming a key enabling technology in the areas of health, mobility, and industrial innovation. So what we would like to see is that the Netherlands becomes a world-leading ecosystem on photonics. And for that reason, I'm really eager to sign this agreement and the start of the Photonic Integration Technology Center, which will certainly accelerate the applications of photonics.
Here is the team. Congratulations. Yeah, here's the team. Congratulations. Cheers, guys. You're live. Off to a great start.
Thank you.
Okay, the team is rushing off to the networking area. And we have come to the end of the event almost, because there are two important things to mention. The first one is, if you can't get enough and you're really enthusiastic for another photonics-related event, the Dutch Technology Week lasts until Saturday. And on Friday, there's an event with the CEOs of Photon First and Smart Photonics. And you can join the event by registering on the website dutchtechnologyweek.com. And now, although we're at the end of the plenary session, the event is nowhere near ended, and maybe the best is yet to come, because we definitely want to invite you to network with us. If you go to the left side of your screen, you saw the chat area, of course, and then you'll also see the networking area. When you go there, you're automatically going to be transferred to an environment called Wonder, which is a really fun and easy to use and intuitive app. Your photo will turn into your avatar, and you can use your mouse, or a pro tip is you can use the keys on your keyboard to just move your avatar into the rooms that you'd like to join. And once you're in the right room, you'll automatically be turning into a video, and you'll be able to have a conversation with the others. So there are 4 rooms in the networking area. The first one is questions to Dr. Michael Lebby, which speaks for itself. The second room is questions to Erik van Geest, who is now rushing over to the networking area to join you there in just a minute. The third room is about the program that Eric just mentioned, which will launch at the end of this month, Metrology. So you can join that if you're interested in this shared research program. And then the fourth room is what can the PITC do for you? So if you want to have any influence on the program, definitely go to that room and join the conversation over there. That's it. Thank you so much for joining us. If you do have to leave, thank you for joining us until now. It was an absolute pleasure to host you. And I would like to end the event with the line that Jean-Paul of Signify said. Let's turn this city of light, along with Twente, into 2 enlightened cities of photons. Thank you so much. Have a great day.